All right, thank you for that introduction, and thank you everybody for coming today. I'm as mentioned, I'm a postdoc in CLASP, so this is a good excuse for me to come down to South Campus, especially on a nice day, to chat with all of you. I'm going to be talking about some of my PhD work, as well as some of the research we've done over the past 2 years here, looking at interpretability and thinking about sort of general models used in the geosciences. I include this image on the left because partially it's sort of, eye-catching, but this is one of the models I'll talk about. There's a compute graph for it that we rendered just to sort of show that there's this kind of inherent beauty in a lot of these models that we work with. And even simple models can be, fairly complex when we start looking at some other inner workings in atomic units. Okay, so EarthML, as we all know, machine learning is a sort of data-driven approach to learning how to make decisions. Remote sensing has been a huge and early adopter of this, but when we're thinking about sort of the Earth systems in general, machine learning has been used for a long time across all sorts of disciplines, from the atmosphere, hydrology, biosphere, cryosphere, et cetera, with all of these, very rich and very powerful tools like random forests, neural networks that we can use across these disciplines. And so we're going to explore some of these ideas today, but for time, I'm really going to focus in sort of on my background, which is looking at the atmosphere and thinking about things like clouds and precipitation. And so, we had a great talk just now looking at the history of a lot of these of machine learning and AI. I hope my graph goes back far enough here in this case. The earliest sort of reference I could find for using machine learning in sort of my area was this K-means paper back in 1964 by Preston and Henderson, looking at the cyclicity of sediment deposits, which was very interesting. But this just goes to show that a lot of this work that I've been doing is not novel. These approaches have been around for a very long time. It's just thinking about sort of new ways to interrogate the data and how we can use it with these very rich new data sets that have come along. Because we're at this very sort of interesting confluence in our field, at least in time, where we've got this explosion in software and hardware, computing resources that are now available, as well as these very large observational data sets, especially from things like spaceborne remote sensing, which has really sort of come online. Spaceborne remote sensing again has been around for a while, but it has exploded in terms of the amount of data available now over the past few decades. And this is a very rich resource for us to feed into these models that oftentimes like to use a lot of data. This just goes to show, especially in areas like atmospheric science or meteorology, we've really seen this explosion in the past few years, and I'm sure this trend has only continued since this was published in 2022. And so I get asked at conferences a lot, right, when we see all of these different machine learning models come up, why don't we just replace all of our, Bayesian retrievals, et cetera, with machine learning, these fancy new approaches? And I always have to say there's many good reasons for that. First of which is just thinking about problem identification in general, right? What are the right questions to be asking here? And do we have the tools that we need to really address them? Would a simpler method be sufficient? Can we get away with a more interpretable multiple linear regression or logistic regression for the problem at hand instead of training a massive, multiple layer neural net that basically performs the same, right, but is much more, much less interpretable. And then are current AI methods mature enough for these types of problems, or should we be sort of thinking about these and how these are evolving over the past few years, and where this might be, where this field might be 5 years from now, for instance? And then say we do have a good problem, it seems to fit, right? Now we actually have to build the thing. We have to curate the training data, which has been brought up earlier, right? This is a huge problem in itself. It's the sort of 80-20 problem thrown around a lot, where most of the time you're actually just trying to find good data to work with, and that you can actually use to feed into your models. Once you get that, then you have to construct the model, thinking about the architecture, tuning it, uncertainties, is it going to be robust? Also very challenging to do all of these steps correctly. And then if you want to deploy this operationally, there's challenges there. Who's managing this? What are the permissions? Is it open and closed source? Who can access this, right? These are important questions. And then finally, where I'll spend most of today's chat talking about is this integration and decision-making step, right? How can we use this as a supplement with current techniques instead of thinking about it as this sort of end-all, replace all, previous methods with this new fancy thing? Can we use these sort of in tandem with previous techniques that have worked well in the past? And then also thinking about ethical concerns and policy issues as well. And then finally, this last idea of trust or interpretability, right? Do we really trust what these models are telling us, or are there sort of internal biases that we need to consider? And so let's think about this idea of trust. And in the previous talk by Dr. Langley was actually a great sort of intro to this, right? One of his last points was talking about how we need to move beyond sort of just descriptions, but try to understand these things more deeply, right? And so oftentimes, ML models in our area have been thought of as these black boxes where their inner workings are really opaque, right? Often the word oracle is often thrown around where you're really often thinking of things in terms of their inputs and their outputs. Oh, it did a great job when I gave it this data. Let's call it a day. Well, I would say that's not sufficient. This can lead to issues with trust, right? This could be an issue, for instance, if there's internal biases in the model that you might not be aware of, but sort of propagate and become more problematic over time. If you're working with a ChatGPT or some LLM and it gives you a slightly incorrect answer once in a while, it might not be the end of the world. But when you're doing flood forecasting or you're trying to parameterize models that have to be accurate up to hundreds of years into the future, right? These issues are hugely problematic and they impact the daily lives of millions of people. So, I argue that we need to do a better job of really trying to understand what these things are doing. And so I want to talk about this in terms of two terms that get thrown around a lot, one of which is explainability on the left here. And this is kind of that black box approach where you're thinking about the model in terms of its inputs and its outputs. It's this post hoc sort of insight where, if I'm changing the inputs this way, that pushes the output in a certain direction, right? And that can be very useful, and that's really a lot of the methods we're going to look at today here is sort of what the approach we've taken. But thinking about shifting towards this more interpretable understanding of our models, moving to this white box approach where we're really trying to understand the internal decision-making process of the model in a human sort of understandable manner. And so let's approach this. This is an AI journey after all, through a few different projects we've worked on with some inverse problems, thinking again about precipitation from surface radars in part 1 here, as well as looking downwards from spaceborne radars in part 2, and then thinking about on the surface, what are the actual precipitating particles looking like, and what are their sort of modes of variability, and can we learn anything from that in sort of an unsupervised approach. So a precipitation retrieval, typically these are Bayesian retrievals where you've got some, information from a radar, for instance, which gives you a tiny piece of the puzzle. I usually describe it as if I gave you a puzzle box, right, 100-piece puzzle and said to solve this for me, and you poured all the puzzles out and there was only 20 pieces in the box, right? How do you figure out what that picture looks like? That's kind of the problem we're working on here, where we have, a variety of different sites across the northern hemisphere for this problem, where we had a collocated surface gauge, which was basically measuring precipitation as it fell, as well as a surface radar pointing upwards so you can see what's happening aloft at that time. And so some of these sites had longer periods of observation, some were shorter, but the idea was to capture these sort of various regional climates, different types of snowfall or rainfall, orographic snow, deep convective rainfall, all of these different types of processes to try to generate, or develop sort of more of a robust model. And we can see, many of the different sites have different structures from the radar, which was good, signifying some regional variability, which was nice. And then we built this fairly simplistic model. It's just a one-dimensional convolutional neural net, right, where we're looking sort of straight up at a point in time in that profile. What did we see in the atmosphere in terms of the clouds aloft, and what does that mean for that surface precipitation rate? And this model, actually, this diagram here is the model that I showed on that initial slide with that, kind of floral pattern on my title slide there. And so I'm not going to get into the results really because I want to talk about more what we were learning from these models. It did a pretty good job overall. But again, we were kind of curious on how it was making its choices. And so there's different approaches to explainability techniques that you can use for these types of neural networks. One of which it's very common you see in literature is the SHAP analysis, which is Shapley additive explanations. And again, this comes down, they're all kind of similar in terms of permuting different inputs to see how that changes your output, right? Another example for this one is if we all went out for dinner, each night in different sort of random groups, and the bill was split, it's just one bill for the whole table. And when you figured out, over time, when you invited me on this dinner trip, the bill was going up, right? And then you realize I'm ordering the lobster, I'm ordering the steak each time we go out. You again don't know exactly how much that, meal was contributing, but you can get an idea that, hey, when you're inviting Fraser, he's, ordering expensive things, and that's pushing the output in a certain direction. And so that's kind of at a high level, a bit of an oversimplification of how this works, but thinking again about it in terms of its inputs and outputs. And so we were curious at what this looked like for our precipitation retrieval. And so what I'm showing here are a variety of different types of precip, so all of the profiles on the left, and then broken down into sort of like trace precipitation, which would be very light, towards more high intensity, very heavy thunderstorms, for instance, on the right-hand side there. And we found some interesting patterns, which was kind of cool. This is the reflectivity data, which is the power backscattered off the particles from the radar as it's looking upwards. Areas not only towards the surface, but also further up in the profile. We think learning about sort of that structure of the cloud and what that means for the precipitation. For instance, how deep is that cloud? Is this a convective system? As well as areas within the Doppler velocity, as we have this sort of funneling towards the right, where we think it's picking up on things like melting layers, where precipitation is changing from, for instance, snow to rain, and what that means for the precipitation rate, which is pretty cool. But this region, towards the surface here, and this reflectivity area towards the bottom, was highlighted. And so we were curious about thinking about this for spaceborne data, which leads to part 2 here. Where instruments like, for instance, the CloudSat cloud profiling radar, which is what I did a lot of my master's and PhD work on. This is pointed downwards, right? This is a nadir radar. It's looking at the profiles of the clouds and backing out information about their internal precipitation rates, as well as how that relates to what's happening on the surface. And if you zoom in on this, it's kind of hard to see here, but there's a magenta band right along the bottom of that top panel there. And this is a blind zone as the signal attenuates from the surface clutter. Just a property of the radar, the way these things work, where you can't really back out what's happening in the cloud there. And this seems like a very fine band, but as we saw in that previous area, this is where retrievals often look, as this is most closely connected to what's happening on the surface. And if you have things like shallow snowfall, for instance, in the top panel where you have this intensification, or virga, where the snow or rain doesn't quite reach the surface, right? It's evaporating. This can lead to huge biases and errors in your estimates. So it's very problematic, right? And again, for deep homogeneous systems, not really an issue, but we get a lot of shallow lake effect, right? So you could be really underestimating and missing all sorts of precipitation in this region. So we knew this was quite important. And so what we ended up building here was a UNet type model, which is sort of an image-to-image model with some surface radar data that we had again in Alaska. And we simulated that blind zone to try to fill that in using the model to see if we could understand, does the model do a better job than traditional just, extrapolation techniques from that blind zone level down to the surface. And so I will show just a couple of results for this because these are images a little more fun to look at. But if you have the ground truth on the left, for instance, and then your typical sort of traditional extrapolation techniques where you just sort of repeat what's happening at that blind zone or that dashed line there down to the surface versus a few different UNets we used, one that just used the radar data and one that used the radar data and some additional atmospheric data from reanalysis. We were able to really reconstruct some of these complex things like these reflectivity gradients where you might have an inversion below the blind zone or an intensification in the other direction where you might previously be underestimating the amount of precipitation. As well as cases that really surprised us were, especially in the multi-channel model where we have that atmospheric data that's being fed into it as well. It's able to look at the sort of the structure of these clouds and then fill in for very shallow events that if you just have nothing happening at that blind zone level, you're never going to be able to predict anything below. And so it was really promising that we were able to see, these complex cases of shallow snow, or as we see in the other case here, virga. And so, these are hand-picked examples, for instance, but and for deep homogeneous systems, the traditional techniques obviously do a great job because that basically extends down to the surface. But, it was curious to see that these more complex units were able to really, pick out these features and do a good job at actually filling in that zone. But again, I don't want to focus too much on the results. We were really curious about what this model was learning as well, right? And so it's this, as a vision, as a image-to-image model, you can look at actual images. So you can look at feature maps, for instance, which is one thing we started with here, to see sort of where the model was looking when it was making its predictions, right? And so for an example on the left here, where we've got this sort of intense area right along that blind zone, and then it sort of dissipates towards the surface. We can see the model was looking at a variety of different sort of cloud features that us as researchers oftentimes would consider as important. So these were things like cloud layers, multiple cloud layers, reflectivity gradients, especially towards that blind zone threshold, cloud edges, sort of where things were positioned in the scene. All of these we know are important for relating, what's happening aloft to the surface, and the model was starting to pick up on these, which was good to see. And then, of course, as you move down to these sort of more embedded or more derived layers on the encoder side of the model, these features become very rich and very useful in sort of improving the predictions of the model. And we looked at a few other, one thing I want to mention in this talk is it's, I think not sufficient to look at just one sort of approach, but it's good to look at a few different types of explainability techniques. So we looked at things like saliency maps as well to see sort of where the model was looking outside of just the reflectivity data, but also the atmospheric context data, which was cool because we saw it was also sort of looking at the wind data to see what that informed it in terms of, the different frontal systems that were coming in and what that meant for the surface precipitation rates. And so, really looking at sort of multiple different types of techniques to make sure that they give you a consistent result was really important here. And just really quickly, modes of variability. One other thing we wanted to look at, this video is not going to play, that's fine, was precipitation happening at the surface. And so we have this distrometer set up at one of the sites where we could actually observe these falling particles. And as these particles fall, you can back out things like their terminal velocity fall speeds, effective densities, particle size distributions, that sort of thing, because we were curious if we could really learn from the data itself to see if it told us anything interesting. And when we did this using some dimensionality reduction, techniques like PCA, for instance, or variational autoencoders, the result here is a UMAP embedding, which is the sort of nonlinear dimensionality reduction. And we were able to break things up into these really unique groups, really powerful groups. A precipitation phase classifier, you might just have something at 0 degrees as saying it's rain or snow, but it's much more complex than that in real life, right? And we were very happy to see that we were able to see sort of these latent embeddings come out. And then we could use these to sort of model and track the evolution of particles throughout the day, which was really cool if we compared this to sort of independent data sets. Okay, so I've talked a little bit about the model development so far and some explainability techniques, but I haven't really gotten to the interpretability part of this, right? Which is, still an issue that we're really curious about exploring. And so this has been, we don't have too many results to show on this yet, but I can go over some of the approaches that we're taking to this, as, maybe to give others ideas for how this sort of framework might work for their own types of models. As we saw, neural networks are very complex. This is another one of those renderings, as I was showing, but for an astrophysics classification model. And while this isn't an exact, a quantitative representation of a neural network, it just goes to show for these huge models with, billions of parameters, it's infeasible for a human to go through and be able to understand how every decision is being made internally, right? And so we see this, and this isn't my technique that I've come forward or come up with, but there's been this sort of movement in the research to look at things in sort of more atomic units, and really zooming in, right? Hooke's micrographia is a great example from, 1666, where he's basically looking at things with a big or magnifying glass and discovered cellular biology just by looking really closely, right? And so we're curious about, zooming in on these perceptrons and trying to look at, why does a neuron have a high activation for a certain set of inputs, for a toy, precipitation model if you're working in atmospheric science like us. But again, this could generalize to other types of models. And so the last few terms I just want to talk about briefly here, this idea of superposition. And so many neurons can react to different types of inputs at the same time, even if they're unrelated, right? You've probably seen this inherently in your models. This property, which they call superposition, is sort of it's sort of what allows the neural network to capture distinct features and more features than it has neurons, right? So you don't need a massive, super complex model in many cases if you've got sort of a simpler problem you're working with. And it's because these models are able to basically take these disentangled hypothetical models and create a much more efficient observed model, right? Where maybe you've only got a few neurons, maybe only 1 or 2 hidden layers. And this is great. It's easier to train in this case, but there's this trade-off that it now becomes much more challenging to sort of interpret, why is that neuron firing for a certain set of inputs? And so an example of this, we get a little psychedelic here. This is an example from an inception vision model, where, giving an example of a monosemantic neuron, which is one that fires in this sort of disentangled model, only for certain, one type of feature, for instance, and then their example here is basically all types of dog faces. This is the visualization they came up with for that. If, all sides of the face sort of at the same time, which is kind of cool. Although I noticed a squirrel snuck its way in there, so I'm not quite sure how that happened in the training data, but the idea is this neuron would only fire for dog faces, and you could say, oh, that's the dog face neuron, right? In reality, you get this polysemantic neural behavior, where instead of firing for just that one feature, they'll often see it fire for things like the faces of cats, in this example, the fronts of cars or the legs of cats. And it's not because there's, some inherent relationship, at least I don't think, between these features, but this is, again, that sort of superposition property coming into effect where you're encoding more features than you have neurons. And so we're currently in the process of sort of exploring this through some very simple toy precipitation models, using things called sparse autoencoders, which Mario, I believe, was alluding to earlier in the first talk of the day. So this really sort of exciting area of research in developing this framework that's model agnostic so that we can look at how certain neurons are sensitive to different inputs, when and where they're firing, and what happens if you disable these features in some test cases. Does that break your model in certain ways? And so just in summary here, as AI becomes more mainstream across the geosciences, trust in these models becomes increasingly important. I believe this, in explainable AI, I don't want to say it doesn't do a good job. As you've seen, we've used a lot of that in our own work. And it provides us with some idea of what the models are doing, but it's not a fully interpretable understanding, right? And there could still be these internal biases causing issues. And so we're really excited about this recent work with the sparse autoencoders and toy models to try to understand these things and figure out if they're picking up actual physical features, right? Is it conserving mass? Is it giving you realistic, unphysical values if you give it some weird inputs, right? Can we see these things? This is really important. And then while it's still an evolving field, we see this as paving the way to more transparent and trustworthy models. Again, the session's on accelerating and thinking about trust, right? To really sort of understand the key physical features within these models. And so we're really excited about where this research is going. Thank you.